Right.
So let me do my share here and then we'll answer number 25 again. So for number 25, they asked us to give us some properties of butane, which is an alkane. It's a gas at room temperature because when you use we know that when we use a butane lighter, you press on the little red button and out comes a gas, not a liquid. So it's a gas at room temperature. The reason it's a liquid inside the container is because it's under high pressure. It combusts. It's colorless. We don't see the gas coming out. It has no odor. And gases that have odors, the odor has been added to it so that people know there is gas in the room and it could blow up. Alkanes are nonpolar. And there's a saying that says like dissolves like. And what that means is if you have a nonpolar molecule, it will dissolve in nonpolar solvents. If you have a polar molecule, it will dissolve in polar solvents. Water is very polar, so we do not expect alkanes to be soluble in water. But we do expect them to be soluble in nonpolar solvents. So the second part of the question is, what about dodecane, which is C12H26? And they want these particular features, and we answered more than that. We said it's a liquid at room temperature because basically from C5H12 on up, they're liquids at room temp. I don't know where the cutoff is where they turn into a solid, but I believe it's above 12. They're colorless, odorless, they combust, they're nonpolar, not soluble in water, and soluble in nonpolar solvents. So the properties are just the same as butane except for the state at room temp. Okay, so for number 27, we're looking at draw the cis and trans isomers of 4-methyl-2-hexene. So I do a zigzag line drawing for the parent. And you can see this as 2-hexene, which means that the double bond is going to start at carbon 2, which is right here where I'm going to draw that little dot. And it always goes from carbon 2 to the next largest number, not 2 to 1. So when they say 2-hexene, it goes to 2 to 3. 3-hexene goes 3 to 4. So I'm going to draw this in, and you can see right away that looks like a trans, right? And if I put the hydrogens in, which I will do in pencil so I can erase them, here's one hydrogen and here's one hydrogen, and they're on opposite sides of the double bond. So this is a trans 2-hexene. Now, where's the 4-methyl going to be? So 1, 2, 3, 4. So this is 4-methyl 2-hexene, but more specifically, it is trans. So to draw a cis, I'm going to show you two ways to do it. I'm going to bounce off of this. And you remember how I put a hydrogen right here, like that?
Mm-hmm.
And a hydrogen, I'm going to put these back in for just a moment.
Mm-hmm.
They're almost like watermarks. But I'm going to draw this molecule because we know it's supposed to be the same except for about here. Now, where do I want those two hydrogens? I want one down like this, and I want one like that. And can you see they're both on the same side of the double bond?
Yeah.
So where does this piece have to go? It has to go where that hydrogen is here. It goes up. So this one is cis 4-methyl 2-hexene.
Yay, I got it right.
Now, another way to draw these is as follows, just so that you have multiple ways of doing it. You could do this, and let's focus on the trans. So we do this, and that ensures that it's trans. And then what do we do with the rest of this? We just continue it. 1, 2, 3, 4, 5, 6. And then here is the 2, 3, 4. This is the 4-methyl. And here, to do the cis, I'm going to do this. Do you see how that puts both of the hydrogens going up?
Yeah.
And then now I'm just going to continue it. If I went down like this, then I'm going to go boom, boom, 1, 2, 3, 4, 5, 6, and I'll do that. So both of these are fine substitutes for what we had done before.
Okay.
And these, it's a zigzag where the double bond ends up being inclined, if you will. Here, the double bond, we just make it straight across because maybe it's easier to see the cis and the trans that way. Fair enough?
Yeah.
So what I'm trying to do here is just offer different ways that may help you to see what's going on and understand it. Okay, so 2 ways of answering 27, and what are other ways of answering 27?
Well, the first ways, the ways you showed it.
I'd say other ways of answering are you could draw all of the atoms
Yeah.
and let's just start that to see what it looks like.
I did because I kind of had to do that to visualize.
And here,
Because I don't
this
have
is
that
just the
practice yet.
start, right?
Uh-huh.
And now it gets real ugly
Uh-huh.
and it takes a long time.
Yeah.
However, if you did want to draw the atoms in, you could do this, and that would guarantee cis, correct?
Yeah.
And here, instead of writing this, you could write CH3.
Yeah.
And here you could write CH3, 1, 2, 3, 4, 5. Oh, that should be a CH2. And then coming off of this guy, a CH3. 1, 2, 3, 4, that's your 4-methyl. So this way is not so bad, right?
Right.
And up here, you could do this. So now you're insured of having a trans, and then 1, 2, 3, 4, 5, 6, and this. The thing that's tough about this is putting the correct number of hydrogens on this at the first go. See, for this, I had to remember, oh, I'm going to put a CH3 there, so I'm going to put 1 hydrogen there. That one's tougher. So the line drawings, all in all, are the easiest. Once you get handy with them, you don't want to go back. It's kind of like a, I don't know. Actually, I don't have a good comparison. But once you get used to it, you don't want to go back.
Okay.
I know what it is. If you've ever had a child and you've done cloth diapers, because it's environmental and all that stuff, and then for a week you feel sick and you don't have time to deal with it, so you go with Huggies. After that week, you don't want to go back.
Yeah, that's probably right.
It's a fact. I've lived that. 29. A hydrocarbon with the formula C5H10 can be an alkene or a cycloalkane. Draw a structure for each of the 6 isomers possible, assuming it is an alkene, and draw a structure for a cycloalkane having the formula. Well, we're going to do better than that. We're going to do all the isomers. So this is 29. We're going to do the alkene isomers of C5H10. So whenever I'm doing these, I just do the zigzag.
Mhm.
And so I'm going to draw the bird because I know that that's 5 carbons. So if I put the double bond right there at the very first carbon to the second carbon, we call this 1 pentene.
And it's 1 because the double bond starts on the first carbon.
Right. We don't tell you where it ends. We tell you where it starts.
Got it.
And we don't tell you where it starts and ends because clearly if it starts at 1, it has to end at 2, and so forth and so on.
Mhm.
Now, what if I draw this? What is this? No, and I'm going to back up. Whenever you draw one of these, you should always ask yourself, can there be a cis and trans here? So can this one have a cis and trans? And the answer is no, because there's 2 hydrogens on the first carbon. And you need exactly 1 hydrogen on that carbon and 1 on the next carbon to have a cis and trans. Do you remember that?
Yeah.
Okay, so take a look at this one. This is going to be called 2-pentene. But is there going to be a cis and trans here?
Yeah.
Yeah, and which one is this?
Trans.
Correct. So if we want to draw the cis, I'm going to draw the same molecule without the first piece there. And on that second carbon, can you imagine that the hydrogen would go straight up?
Yeah.
So on this second carbon, I'm going to make that methyl group go straight up. And that does look like a cis, doesn't it?
Mhm.
Now, the book says that there are 6 of these. So
6
let's,
alkenes.
pardon me?
6 alkenes isomers.
6 alkene isomers, yeah.
Okay.
So naturally, what I want to do next is I want to move the double bond over to here.
Yeah.
But if I move it over to here, isn't that a 2-pentene again?
Yeah.
Okay, so I can't do that. So what do we have to do now? Now we do this. And that.
Okay. So we
Okay, so
added branch.
this looks like it's going to be a butane, right?
Yeah.
So I'm going to put the double bond here. Wouldn't this be 1-butene?
Yeah.
And what would we do? We'd say 2-methyl 1-butene.
Oh, the branches go first when naming. Right. Because butene is referring to the parent. So yeah.
Yeah.
Okay. 2-methyl.
And what else could I do here? Could I put the methyl group here and have a different molecule?
No.
Well, let's name it and find out. What's it called? 1-butene, right? Where's
Oh,
methyl?
on 3.
Okay, so are these 2 different molecules that I've just drawn?
Yeah.
Absolutely. They are different. And we know they're different because we named them correctly and they have different names. Okay, now does the double bond have to be from carbon 1 to carbon 2? Could I do this instead?
Yeah.
Okay, that's going to be a 2-butene, right?
Yeah.
Now, where am I going to put that other carbon that I have to put on here?
Either on 2 or 3.
Well, if I put it on 2, isn't it the same as putting it on 3? Because here, this is putting it on 3, but now that's 2. And the reason it's 2 is we can number this left to right or right to left. We want the ene to be as small as possible, but also we'd like the substituent to be as small as possible too.
Mm-hmm.
So we don't want to number this and call it 1, 2, 3 and call that a 3-methyl. We'd rather go 1, 2, 3 and call that a 2-methyl. So these are the same thing. And this is going to be a 2-methyl butene. Now let's take a look at these. Can any of these be cis and trans?
Um,
How about that first one, 2-methyl 1-butene?
no,
Why not? You're correct. And why not?
because there's 2 hydrogens on that first carbon.
Bingo. How about the 3-methyl 1-butene?
No, for the same reason.
That's correct. How about the 2-methyl-2-butene?
Hmm. I think so.
The answer is no,
Oh,
because you need exactly 2 hydrogens bonded to those 2 carbons.
yeah. I
And
would draw
here
that one out.
you have a carbon, and a carbon, 3 carbons and 1 hydrogen. So it's not going to work.
I see now.
Fair enough?
Yeah.
So these are the 6 alkene isomers of C5H10, 1, 2, 3, 4, 5, 6, and their names.
Okay.
Now I said we were going to do one better than the book. It said draw one of the cycloalkane isomers. We're going to try and get them all, okay?
Okay.
So this is 29B, the cycloalkane isomers of C5H10. So when you're doing these, you always want to start with the biggest one possible, meaning the most number of carbons in the ring. So even though this isn't a circle, we call that a ring. This is called cyclopentane. So the parent is actually cyclopentane, and the parent is the biggest, is the ring. Now, if we make the ring one smaller, we only have 4 carbons, but if we add a carbon as a substituent, we now have this thing, which is called a methyl group. Which carbon is that methyl group on?
Depends.
1, 2, 3, or 4?
It could be either.
No, it's on 1.
Oh, how come?
Because the substituent always goes on the lowest numbered carbon if you can do it, right?
Oh, yeah.
Okay, here, what carbon is that substituent on in the second drawing?
1.
Carbon 1, because all I did is I rotated this 90 degrees, right? That's it.
I see.
So these are the same thing. Carbon 1 is the one that this guy is on.
So is it
Okay.
1 cyclobutane?
Well, we only call it methyl cyclobutane because there's only one substituent. Do we need to tell people that it's on carbon 1?
I guess not.
We do not. If there's 2 substituents, then we need to start telling people. Because if there's 2 substituents, they could be both on 1. One could be on 1 and one could be on 2. One could be on 1 and one could be on 3.
Yeah.
Okay. So now we cut it down to this, and I'm going to do this. Is this 5 carbons?
Yeah.
And it does happen to be 10 hydrogens. So this one is called ethyl cyclopropane. Now we could do this. Now this one we have to call it 1,1-dimethyl cyclopropane. And the reason we have to do that is because there are 2 substituents. They do not both have to be on the same carbon. So far we have 1, 2, 3, 4 isomers. Now the next one, there's actually 2 isomers. So notice we're getting isomers here without regard to whether they're structural or geometric, right?
Yeah.
So that's why we included cis-trans. Those are geometric isomers, but we included them. So we're getting all the isomers. Now I want you to imagine that this triangle here is this blue whiteout, if you will.
Okay.
Now, if I take that triangle and I change it to this, we're looking at the end of the triangle, the flat end of the triangle right here. Are you with me?
Mm-hmm.
So I'm going to draw that over here. And I'm going to draw it like it's like the edge has some sort of thickness.
Okay.
And I'm going to draw it twice. Now, what is the geometry around this guy? It's supposed to be SP3, right?
Yeah.
Which means it's supposed to be kind of tetrahedral, right?
Yeah.
So to make this look tetrahedral, I'm going to have something like that. Does that look kind of tetrahedral? Because this bond is going away from us. This one's going straight across. This one's kind of down and actually towards us a little bit. And this one's coming up and towards us a little bit.
Okay.
Okay. So if I put a hydrogen here and a hydrogen here and a CH3 here and a CH3 here, another way to draw that would be this. These are the same thing.
Okay.
I could also draw it this way. I could put a CH3 here and a CH3 down here, right?
Yeah, so it's trans.
Okay. Can these guys rotate and turn into the other? And the answer is no, because it's stuck in a ring.
Right.
So this would be a cis and this is a trans. And the way you would draw this one below would be this. So we have 5, 6 isomers. And I'd like you to come up with these 6 if possible. There's a 7th that I'm just going to tease you with and say, there's the 7th, but I'm not going to show it to you.
Okay.
You wouldn't be responsible for it.
Okay.
You do want to know now, don't you, though?
Is it like the chair?
No, yes and no. I'm going to show you the 7th isomer, okay? So here I'm going to put quotes 7th. You're not responsible for it. Here it is. Does it look like that one?
Yeah.
Okay. If they were exactly the same, you should be able to make a model of that one and a model of that one and see that they're exactly the same. You can line them up side by side and say, oh, yeah, on this side it goes down and on this side it goes down. But if we line these up, can you see on this side it goes down and this side it goes up?
Yeah.
That's not the same. So then you might say, okay, I'm going to rotate this to over here. And if you rotate that to over there, where does this rotate to? In the back, right?
Yeah. Oh, I see. Yeah.
Okay, so this is going down and this is going up. Does that match that?
No. Oh,
Does that match that?
that does.
Yeah. Does this in the up in the back match this up on the left?
No.
No. Okay, so I'm kind of convincing you that rotating it doesn't work, right?
Right.
But it's hard for me to convince you that flipping it over doesn't make it work either. So you have to build the model. And what you do is you get a piece of cardboard and you stick toothpicks coming out of them, one up and one down. And you use cardboard because it's more rigid than paper, right? And then you make this is considered to be the mirror image of that one. And then you make this model and then you see if you can get them to line up just the same. And you never, ever will be able to. Whereas if you take this guy and make this guy, you can get these guys to line up very easily. You just flip one over.
Yeah.
You can kind of see this one's easy to see. You just flip one and you got it. So here's the secret 7th right here. And you get to learn about stuff like this in organic chemistry. It's really cool. These two are called enantiomers. which means they are non-superimposable mirror images. And in organic chemistry, the example they give you for non-superimposable mirror images are these. So if you imagine there's a mirror between this hand and this hand, what would this hand see in the mirror? It'd see this hand, right?
Right?
But this hand is not this hand, is it?
No.
And if this hand could reach through the mirror and grab this hand and shake it, you go, wait a minute, that's not a normal handshake, because they're not the same,
Yeah.
right? So that's the story with the thalidomide, is it had two molecules, one left-handed, one right-handed. One of them caused birth defects, the other one cured morning sickness. But the problem with these two hands and molecules is that they're nearly impossible to separate. The only way to separate them is if you use a molecule that has handedness. Because if you, this sounds gross and disgusting, so I'll make it less gross and disgusting. Let's say that you worked in some shop where they made hands like this out of wood. Okay? Would you be able to distinguish between left hands and right hands by going in with your right hand and shaking it like a handshake?
I feel like you could.
You certainly could, because you know it would fit in with the right hand. You go, oh, that one fits. You put it in the right hand pile. That one doesn't fit. You put it in the left hand pile. You can do that with your hand because your hand is chiral. Now imagine you didn't have your hand because you had lost it in some industrial accident and you're sticking your stub in there. It'd be hard to tell if you had a left or a right. With me?
Yeah.
Okay, so that's the deal. You need handed molecules to separate handed molecules. And that works really well for organisms because most of our molecules are handed. So they fit together. And that's, I think, where I started going off on that story, where if you went into another universe where it was the other hand, you'd starve.
Yeah, we talked about that a little bit.
Yeah. I mean, it would make a great science fiction story about, you go into a parallel dimension, but it's got instead of L amino acids, you're using R amino acids, and you die because even though you're eating food, your body cannot assimilate proteins out of it because you got the wrong catalyst.
You should write the book when you retire.
Have you seen my writing? It's chicken scratch.
That's not that bad.
I can't put words together.
Not that bad, Tony.
I've got the great idea. I need a ghostwriter. How are you at writing? Okay, well.
Not anything, not science fiction. No way.
Then not you. Okay.
Okay, I should get off. It's almost 2 anyways. I have a meeting at 2, so.
Okay, so we did that.
We did.
We're good with 25, 27, and 29.
Yeah.
Fantastic. You have a good meeting.
Okay, thanks.
Bye-bye.
Bye.